Hello, my name is Joachim Schiele. I'm the head behind libnix, and today I think it's time to do an introduction into what it actually is. It's an effort sponsored by NLnet so far, and it aims at two fields, basically broader Nix support and also Nix on Windows. And we should probably start with answering the question, why Nix in the first place? And the answer is pretty simple. It's a purely functional languages, so output depends only on declared inputs. This is important if you do a make derivation. So you get deterministic evaluation. Then we have immutable store, which means everything inside the store where all the software lives is hash-based and usually never modified unless it's created by the Nix build user. We have complete dependencies. Every dependency must be explicitly declared and is fully tracked. This is true during build time, but also when the software is being deployed to various machines. And we have also build isolation. This uses sandboxes, and this is pretty old in Nix, but it is still new for programming language and software engineering as a rule, I think. Builds only see declared inputs, preventing accidental system coupling. So that's also very important, so that you don't put parts of your development environment inside the build box, and then when you ship it, it breaks. So basically, these features, I think, are the most important features why Nix is a cool language for this kind of effort. And also the gaining in popularity. You see that this is the star history on the GitHub repository, and you see that there's like an exponential growth during time. So this is 2014, this is 24, like 2 years ago. And as a side note, when I visited the NixCon in Darmstadt, I was actually pretty upset that there was not much more innovation during the time I didn't do any Nix code, because when I left Nixcloud, basically I didn't look at any Nix technology for a few years, and coming back I realized, well, there's something deeply wrong with the way we use Nix nowadays, because I assumed it would be a much bigger movement by now. I assumed that there would be IDE support and major industry players would be doing lots of Nix stuff. Instead, what I've seen that there's still like startup activity from San Francisco. So basically, Nix was popular in the US, and there was no major pickup in the Europe space for Nix technology. And also, if you take this graph here and you print the star numbers of popular languages like Python or C, C++, then this exponential growth rather seems to be a linear curve, I guess. It would be more looking like this. And this also means we're decoupled from other languages, yet Nix is usually used for deploying software. So where's this gap coming from? And I think we can already state that Nix is a great and successful concept, but after thorough analysis, I think one of the major things which keeps Nix back in deployment is the wrappers you use, like wrappers like Cargo to Nix. They are really hard and they constantly break. And also Nix is for Unix only, so you have pretty good support on Linux, especially on NixOS obviously, but then there's some macOS features. For years there was like the support was a little laggy. I think it got better, but still Nix is not on Windows. And as I stated on the blog post, I think that many of the projects which would also decide to use Nix, when they see it's not on Windows and there's one team member which uses Windows, then they basically can't use Nix and won't use Nix. So what now? So my proposal is that libnix fixes that, and we're gonna look at how it's going to do that. So libnix has two requirements. First off, Nix must be available native on each platform. So on Linux it is, on macOS it is, but on Windows it is not yet. So the important bit being use same abstraction for different OSs. And this was like number one. And number two, use Nix as a library. That's why it's also called libnix. And in that scenario, I extended cargo with a Nix backend. So basically, if you run cargo build, it will use Nix in the backend, and you're not using any language wrapper. And the resulting binary will be built in a sandbox, and it will be also in /target/ debug / your binary name, but it will just be using the Nix backend. So basically, we have a Nix build system, we use the Nix store, we have sandboxing, and we have a native toolchain. Basically, it builds on top of Nix packages for Linux. Maybe in the future we're gonna have a Win package of some sort. That depends a bit if the Nixos folks, if they're okay with going away from Bash. But if they're still like reluctant to do that, maybe a fork of some sort might be a good thing. But the question is, this was talking about Cargo and Rust. What about other languages? And for this, I want to look at the popularity graph on GitHub. So during the years, there was an increase in Python usage, and this is mainly driven by AI and data sciences, and it's a good thing. But Python is quite hard when you want to do it with Nix. So basically, most of the AI deployments I see nowadays, they have lots of Python code, but it's not even clear on which platform they are supposed to be used. Is it Linux with CUDA, or is it Windows, or is it a mixture? Then there's JavaScript and TypeScript, which are basically the same languages, and they're still quite popular because they're running like most of the software in the web browser. We still have lots of Java around, but you see it's decreasing. And also, when it started here, it was clearly Java, but nowadays I think it's more a JVM-based language. So there's Scala and other similar forks of Java. Then we have C#, of which I cannot tell you very much. And C++ and C, they're still around, so C is pretty stable. C++ seems to be also pretty stable. There's a few newcomers like Go, which for the dependency and deployment side, I don't like Go very much. It's cool if you do it with containers. It's not so cool if you want to do it with Nix. And then Ruby on Rails kind of derailed, and Objective-C was probably replaced by other UI languages, probably TypeScript and JavaScript, plus some native UI tools like Swift, for example. Okay, so but what do have these programming languages in common? And I think this diagram shows it pretty well. In the center, we have all the source code. So basically, if you develop for any of these languages, then you're gonna host your source code on something like GitHub or GitLab. Then parts of your source code of your project's gonna end up in the registries. So say, we just pick one here. Let's do crates because I'm most familiar with the crates. So say you're doing a Rust project, then you would upload some crate on crates.io, and then other people can use your library, which is nice. Like this part of the registry, it uses the metadata of your source code, like dependencies in cargo.toml, and this helps other developers to understand what stack you are using for your library and how to integrate it in their project. So in the end, Rust projects tend to have from 200 to 400 dependencies for bigger projects like Cargo, and these dependencies are kind of built in the deps folder for dependencies. So basically, the programming languages, they have a way to host the source code. They have a registry with metadata, and basically there are some support tools. And for Rust, it's the support tool is Cargo. You use it to manage your project and the dependencies. It manages the compile step, and basically in the end you get a Rust source code base compiled into an ELF binary, which you can run on Linux. Same is true for other languages. For example, in the case of JavaScript, there's 3 tools which basically do the same thing. In Python, it's a bit of a special situation. So there's Anaconda and there's PyPy. Both are, I guess, pretty popular. For the upper one, registry, you would use Conda. For PyPy, you could use the PyPy binary. And there's also UV written in Rust. I think it kind of strives to replace both of them. And maybe in the end, it's gonna have a new registry as well. At the moment, it doesn't. And then let's look at how the languages like C and C++ do. So if you're from the Windows developer side, you're probably using VC package. If you're from the Linux side, you're probably gonna use Conan. And basically, those tools, they're not like Cargo. They have semantic versioning. They do some sort of build and project management, but as C and C++ tend to have so many different ways of build systems, VC package, for example, can do solutions and can do CMake, but then there's like scons and other tools which are used to build C and C++ project. So that's not as straightforward as one would wish to program in these languages. And then on the Nix side, basically the source code and the registry is kind of like managed from Git. It's in this repository called Nix packages. And if you are using this, you can either do this from a Nix flag, and then you can decide the version of Nix packages you're going to use. You can use the Neve tool to do basically the same for non-flake things. So kind of this was before flakes. And then you can basically decide on dependencies inside your Nix project. And if you do NixOS, which is Nix plus systemd, then you can also include software into your operating system with the system packages. And this is done mostly manually. So there's not something like cargo at serde, which would add it to your system packages inside the configuration.nix, but instead this is done manual. And I think this is a good broad overview of the system languages we have nowadays. So if you think about the project layout, I want you to think like this. So basically, the source code you own, your source code, you can consider this open source, not in a license sense, but in the way you can work with the source. It's easy to modify, it's in your control, you understand the inner workings, and this is in contrast to the libraries, where it's usually considered closed source, out of your control, and complicated internals, which you don't want to understand at all. And if we continue this trend, there's a few common patterns among all these different tools you can use. I think the most important thing is the semantic dependency resolution. It helps you to manage dependencies, and usually they also come with a log file nowadays, so they basically pinpoint down all the dependencies you want to be using, and so on a different machine you would get the same result. And example would be cargo at serde to add a library into your cargo project, and then it's also logged. The build environment, that's another common pattern, and every language like Cargo, like VC package and so on, they all tend to create build environments, and in the Nix space we also have sandboxing for that. The build environments also do the downloads of the dependencies. They stage the Rust C compiler so that you can do incremental builds. That helps you to reduce the build times. And you have build caches. And usually there's some command like cargo build. Then there's a common concept of formatting and linting. And even more important is the registry. So basically, semantic versioning also only works if you have good registry support. Then your project needs to have a manifest like the cargo.toml. The registry should be downloadable so that you can use it for offline computation of dependencies. And it should have a way to manage packages on the registry. So if you write a library, it would be going with cargo publish. Then your programming language should have something like tests. So you can run cargo test. Sometimes maybe tests run in a sandbox or even in a VM. The Nix tests are pretty cool in that regard. Today's programming language also come with a garbage collector, so that you can basically clean the project artifacts, which often are all over your operating system. In case of cargo, this is cargo clean. And then when we go to build caching, there's concepts like dyscc, ccache, and Nix binary substitutes. And this is also a common pattern among many of these programming languages. And there's external dependencies. In case of cargo, this is called the builder-as concept, and this is used to find C libraries in your operating system. It can also be used from other languages, like if you do Go, then it's called CGo. In C++, you would use the C interface. If you do Python, there's CPython, and if you do Node, there's NodeJib. And basically, all these concepts are there, so you can use system libraries, but from the language you desire to programming in. There's also code generation, like protobuf and whatever code you want to generate, like dynamically can generate code. And this is all done in Rust with this builder-as pattern. So basically you have a builder-as file, this is compiled and then executed in the run phase, and then the crate, when the crate is compiled, it can access these generated artifacts. Okay, so when we look at how today's projects work, basically you clone your source code to your local directory. In the Nix case, you do a Nix develop. Nix develop has some limited form of log file support, which goes for most often for things like Phoenix, which is your Rust toolchain. It goes for Nix packages and some other tools you're gonna use. And it uses the Nix store, which is already great. But like most of the projects nowadays, they go then into what I call the ultimate clutter phase, where you then just type make, or you do cargo build, you do Conan build, or Mason, or a configure if it's auto tools, or CMake. And basically from there on, you end up in having all these directories used all across your machine. Some are in your home directory, some live in the project directory, and some even live in the system directory. Some write to temp tiers like /temp, and the problem is who cleans up this stuff. The biggest problem is in the first place to know that this stuff actually exists. And for libnix, I modified cargo in a way that it uses Nix, and this is called the cargo backend. And basically, that's the recommendation from me. It does fine-grained Nix store support. Root crates are compiled into the Nix store. All the dependencies are downloaded in separate Nix store directories. The deps built in Nix store directories, and also the registry in future will be downloaded into the Nix store. So basically you have a few very lightweight symlinks into the Nix store paths, which you can use to prevent garbage collection. But in the end, like most of the stuff can be then deleted and cleaned up by Nix collect garbage. Other advantages are you have fine-grained log support. The caches will also do old dependency, so that when you in your project decide to try a new dependency for a certain cargo dependency, for instance, and you just switch back, then the old caches are still there, so compiling will still be quite fast. With cargo in particular, you always have out of source builds. With C and C++, sometimes you don't, sometimes you do. And you also have full incremental Rust C support, which means compiles for the same target will be pretty fast. In regards to distribution, intermediate build artifacts are shared. This is a great plus. Dep downloads are shared. So at least on your local machine with various projects, these downloads will be done only once because of the Nix nature. And of course, you will have complete dependencies. So these are basically the two worlds. And from the linking perspective, this might also be interesting from a historical view. You have inner app linking, and this is usually the decision between dynamic and static linking, and often comes with a choice of bundling libraries. In Rust, this is a common thing to bundle C libraries into a Rust trait and then compile it on the fly. Traditionally, using dynamic linking and then also distributing the dynamic libraries into the system folders, this gave us DLL hell. Or in the Debian world, it meant unmeant dependencies. And a feature which was created to have a better memory layout and to reduce the memory usage ended up in wasting millions of hours of administrators in keeping the system sane. And from an inner app linking perspective, there's also this Linux linking aspect we should look at. Traditionally, we always were using glibc. glibc was mainly, from the license, was mainly motivated you to do dynamic linking. This also means, however, that if you want to distribute your program, you would also have to distribute the glibc as well, which is hard. Then came Alpine Musel. This is basically also a libc implementation with the focus on static linking. So you get one big binary. And then a very new language, this is SIG. I think it's very interesting. I came across that when I was listening to Chris Jenkins' podcast, Developer Voices, with Loris Crow as a guest. So they discussed that SIG basically implements libc features on Linux. So it doesn't use any glibc. And there's this quite cool project called SIGbuild in Cargo, which lets you select a certain glibc version which you want to be backward compatible with, and then it will basically build all the artifacts into your one binary application for deployment, and will be compatible to a certain glibc version without even touching any glibc header. So these are the two worlds: inner app linking, Linux linking. But then we also have to look at cross-platform deployment. So nowadays, Flatpaks are gaining popularity because they're just easy to install and to match. And I think for commercial products, which are mainly closed source, this is the best format to distribute to Linux. In a way, we could also use Nix for the same purpose. Nix doesn't require you to be open source, but it requires that someone modified the source to compile with Nix in order for you to distribute the binaries. And in between, like nowadays a legacy solution is Docker, which I will discuss in a third detail later, but it's also an important platform for deployment, mainly for the server side. Okay. Then other than the way you distribute applications, it's also important to look how you distribute them. And there's this concept of immutable file systems and atomic distributions. And traditionally, the first thing people had experienced this was snapshots on the file system level. The virtual machine would be immutable during use, but you always could snapshot them. This works to some certain degrees. Also for legacy reasons, we had LXC and systemd nspawn. And on Nixos, they're pretty cool because they support shared Nix stores. So you can wrap in a subset of your Nix store into the container, and the containers will then only see this subset of your store and execute the programs in isolated environments. And from the same concept, like with the shared Nix store, you can view Docker. So Docker gained popularity because you have this one Docker file, and this is evaluated line by line. And each line executed will append to a binary tree, which means If you do the heavy lifting first, like installing a certain set of software on a Debian Docker image, then it will download this once, write it to the binary tree, and then you do all your custom modifications on the image, like how you use the toolchain for your project in a later stage of the same Docker file. And the cool thing is that it will, if you don't change the first few lines, it will never execute apt-get update again, which means it's quite safe. Because sometimes if you evaluate all the Docker file 2 years later, it wouldn't even build because the upstream projects just moved artifacts around and apt wouldn't find the required binaries to download. So this is kind of like a snapshotting system on a Docker file line-by-line basis. Some more modern approaches to having a immutable file system are libOS tree. This is popularized by Red Hat employees. It's a Git-like system for versioning updates of Linux-based operating systems. I think all in all, this is a cool thing. And maybe we could use that more in Nix, not as a store replacement, but for other things. For example, we could maybe have something like line-by-line execution in make derivations, and then use libOS tree to basically memorize the different stages. But that would be something for the future. Another approach would be the immutable file system by the Steam Deck. It's read-only, and you're not supposed to change anything. You're free to change that, but then you basically enter a liability because updates could break, and it's more considered a hack. And now that we've seen all of the legacy approaches to the problem, let's see how Nix Store helps to make things really awesome. Because in the Nix Store you have the capability to add a new entry into the store. Nix Store is just a bunch of software with a make derivation, and the result is being hashed and then written to a special directory. For normal usage, it's just read-only, but for the Nix build user, it's read-write. So, I mean, you cannot change a store entry which already has been done, but you basically can create new ones. And this is mainly used on Nix and NixOS, while all the other things are mainly used on Linux. And Nix runs on Linux, so I think if we make the Nix store to run everywhere, we could basically get rid of most of these solutions and just use the principles which are introduced by the Nix store. Okay, then have a brief overview about a posting of mine. So if you want to see this, that's the URL. It's basically introduction on the libnix initial idea with some numbers, some statistics on Windows users of on the desktop machines, and the basic takeaway from me to show this to you again is we need, in order to fix this problem, we need to port Nix to Windows, and we need to integrate Nix into the package manager backends. So that's the key takeaway. And here it's discussed why this is a good idea. If you want to read it, you're welcome. The Windows part with Nix on Windows, in another posting, which came a bit later, I outlined the work from Wolf, Nix community member, who during 2020 had a working Nix Windows release. He did this all for himself. The code is available, but the Nix community didn't pick this work up. That was even before Windows 10. But my analysis of Windows 10 and more recent Windows versions showed that there's basically nothing in the technical space which keeps us back from porting Nix to Windows. The path length restrictions have been overcome. The case handling for paths and files per directory, like capital case, can be changed. There's directory and file permissions now with user and group. We have proper symlink support. You need to enable this, but it works once you have enabled it. And there's even Unix domain socket support. So basically, the only thing which limits us in doing this is we need a fund and we need capable people doing this. And there's already a few people implementing this, like John Erickson, for instance, who's very capable, and I think has done a great job in preserving the source code base, and then also started to integrate chunks of it into Nix. And basically his mission is to get all the support into Windows. And then from the libnix in a package manager perspective, I've created a prototype with cargo. And the current status is that there's quite a bunch of software we already compile quite good. There's a screencast of the cargo build with a backend, so you can look at it. It's on this URL. There's going to be an update soon because I did improve it with some majorly cool things. And I just want to have another brief introduction why it's better than using wrappers. So basically, traditionally, this would be this case here. You would do the cargo build, you compile a release, for instance, and then when you're happy with that, then you would do the same thing over again with the cargo to Nix wrapper. You add a few hacks, supposedly, and then you compile again, and then you do the deployment with this result. Okay, not with this result. And if you can use libnix inside the cargo, then it's basically a cargo build, as you would always do, minus release, and then you can instantly deploy this artifact if it builds. So that's the major difference. And we could have this for basically any language. And this is a screenshot of how it looks when you're doing it. So basically, at the moment you do this cargo backend equals Nix thing, and then you do cargo build, and then you see that there's some disclaimer, and that also that it uses the Nix backend. You see that there's some compiling. You even see the warnings. And during this work, it was very important to have the messaging to look like they came from cargo, because cargo has actually a quite neat way of displaying messages and warnings and errors. And I try to retain this, even though the backend it creates, the Nix backend, the Nix build system it creates is basically a huge set of Nix files which are evaluated in one go. Okay, but in the end, when the result is written, it writes to targeted by cargo, and the symlinks then look like this. The future. I think for the Nix community, we should tie our success to successful languages. And I picked cargo because Rust is just great, but also because the code base is pretty clean and easy to work with. That's point A. And point B, we must port Nix to Windows so that there's no people who can tell us Nix is not an option for this platform or like for our project, because we sometimes also release on Windows or have developers on Windows, and so that they cannot just not pick Nix for that reason. Okay, so huge thanks to Anelnet for funding this work, and I think it's actually really great to have the means to produce a prototype with cargo, with the Nix backend, and to show how this works and that it works well. It's also fast. And if you're interested in details, or if you want to have this in your commercial product, please contact me. Here you can reach me on X. Or if you just want to read the results from the NL-funded research, then this is the URL. Either way, I wish you the best, and I hope you enjoyed this short introduction into libnix and my thoughts on Nix. Have a nice day. Bye-bye.